Welcome to the deep dive. We're here to plunge into some pretty complex topics using the sources you provide to really pull out the most important, maybe surprising, and sometimes, mind-bending bits of knowledge just for you.
That's the goal.
And today we're really venturing into something that, well, it sounds like it's straight out of a sci-fi movie, but its roots are actually like as old as geometry, fractals.
Right, fractal.
Yeah, think about those, infinitely intricate patterns, like a snowflake maybe, or the way a leaf branches out, or even just the jagged edge of a coastline. These aren't just, pretty pictures. They're apparently governed by some pretty deep mathematical ideas, self-replication, things like that.
Exactly.
So I guess the big question for this deep dive is, what actually happens when you take this, timeless mathematical beauty and smash it together with the raw power of modern AI?
Yeah, it's a really, really captivating mix. Our deep dive today, it's all centered on fractal hybrid AI image generation. We're going to try and unpack how AI is, learning to create some truly stunning visual forms. And it's doing that by drawing inspiration, sometimes quite deep inspiration, from fractal geometry.
So it's not just about making cool art then?
Well, that's definitely part of it, and a really compelling part too. But it's also about grappling with the challenges, the really fascinating challenges, and looking at the future possibilities.
Right.
What happens when this intersection of pure math and advanced computing really starts to take off.
Right.
And we've specifically tailored this whole exploration from the research notes and articles you sent over. So hopefully it offers you a direct way into understanding this field, which is, complex and moving fast.
All right, let's really dig in then, because, many of us have probably seen fractals as sort of mesmerizing, sometimes kind of trippy computer graphics. But what are we actually talking about when we say fractal? Is it just a pattern? Or is there something deeper mathematically that AI can actually, understand and use?
That's absolutely the right place to start. Fundamentally, fractals are these intricate, often irregular, and infinitely complex patterns. They really break away from the smooth, predictable shapes we learn about in, standard Euclidean geometry.
Well, like circles and squares.
Exactly. Their defining thing, the key property, is what we call self-similarity, or more formally, scale invariance.
Self-similarity.
It just means that no matter how much you zoom in on a fractal, the parts still look basically like the whole thing. So unlike, say, a smooth sphere, if you zoomed way in, it would just look flat, right?
Yeah.
But a fractal coastline, for example, the closer you look, the more jagged detail, more complexity pops out. It always keeps that characteristic rough look at every single scale.
Right.
There's this famous example, the coastline paradox, that really illustrates this.
The coastline paradox?
Yeah, it basically says that the measured length of a coastline actually gets longer and longer, technically without limit, the smaller the measuring stick you use, because you keep finding more and more little wiggles and bumps.
Wait, really? So the more precise you are, the longer it gets? That's genuinely weird. It's not like measuring a table.
Exactly. It completely flips our everyday idea of measurement on its head. It shows that endless unfolding detail.
Okay, that is mind-bending. So these unbelievably complex shapes, how do they even come about? Do you need, super complicated instructions to make them? Or is it simpler than that?
That's the amazing part. Often it's the latter, that seemingly infinite complexity. It frequently emerges from surprisingly simple recursive rules.
Recursive, you mean like repeating the same step over and over?
Precisely. You just apply the same basic instruction repeatedly, iteratively, and out of that simple loop pops this incredibly intricate, detailed pattern.
Wow.
Think about the really iconic examples like the Mandelbrot set and the related Julia sets.
I think I've seen pictures of those, the swirly, psychedelic-looking ones.
Those are the ones. They're generated by just iterating really simple math rules in the complex number plane. You take a starting point, apply the rule, take the result, apply the rule again, and again.
Okay.
The patterns you see are basically visualizations of how quickly or slowly those numbers grow under that repeated process. The Mandelbrot set itself is kind of famous for acting like a map for all the possible Julia sets.
A map? How so?
Well, the shape of the Mandelbrot set, especially its really intricate boundary, tells you something about the corresponding Julia set for a given point. Like whether that Julia set will be a single connected piece, or if it'll be shattered into a whole mess of disconnected points, like dust. Sometimes they call it fat 2 dust.
Fat 2 dust. Okay. That's quite evocative. So Those are generated by these simple iterative rules. Are there other, maybe simpler to visualize examples of fractals that really show this self-similarity thing?
Oh, absolutely. A classic is the Sierpinski triangle.
Right, the triangle with holes in it.
Exactly. You start with a triangle, cut out the middle triangle, then do the same for the 3 remaining triangles and just keep going. It's a really clear example of self-similarity. The whole thing is literally made of 3 smaller, identical copies of itself.
Okay, I can picture that one easily.
Then there's the Cantor set. It's a bit more abstract, but fascinating. You start with a line segment, remove the middle third, then remove the middle third of the remaining 2 segments, and so on, forever.
So you end up with dust again, like the Julia sets.
Kind of. You end up with something that has, paradoxically, 0 total length because you keep removing pieces, but it still contains an infinite number of points. An uncountable infinity, actually. And its fractal dimension, which we'll get to, isn't an integer. It's somewhere between 0 and 1.
0 length, but infinite points. Math is weird sometimes.
It really is. And for something that looks more, well, organic, there's the Barnsley fern. It looks incredibly like a real fern leaf.
Yeah, I've seen that one. It's uncanny.
And it's generated using a formal mathematical system called iterated function systems, or IFS. It shows how natural-looking patterns can come from very simple math rules within this IFS framework.
Iterated function systems, IFS. Okay, that sounds like the mathematical engine behind some of these. How do they actually work to make something like the Barnsley fern? Is it random or is it deterministic?
It's a really elegant mix, actually. And IFS is basically a set of contraction mappings.
Contraction mappings, like shrinking things.
Exactly. They're geometric transformations, shrinking, maybe rotating, shifting, but they always bring points closer together. That's the contraction part.
Okay.
When you apply these transformations over and over again, iteratively, they are guaranteed to converge to a unique, specific shape. That shape is called the IFS attractor, and that's the fractal image itself, like the Barnsley fern.
Guaranteed. How?
There's a mathematical theorem involving something called the Hutchinson operator that formally proves it. It shows that these systems will converge to a unique, self-similar fractal. It's not just hoping it works out, it's mathematically certain.
Okay, that's reassuring. So how do you visualize it? Do you just run the math?
Well, one really cool, intuitive way, especially for IFS fractals like the fern, is called the chaos game.
Chaos game. Sounds fun.
It kind of is. You start with just a random point anywhere on your screen. Then you randomly pick one of the IFS transformations, one of the shrinking rotating rules, and apply it to your current point. Plot the new point. Then you repeat. Randomly pick another rule, apply it, plot the point.
So you're just jumping around randomly based on these rules?
Yeah, seemingly randomly. But if you do this thousands or millions of times, the plotted points gradually build up and outline the exact shape of the fractal attractor. The hidden structure emerges from these random steps. It's pretty amazing to watch.
That is wild. Randomness creating perfect structure. Okay, so that's IFS.
Yeah.
But you also mentioned visualizing the Mandelbrot and Julia sets earlier. They look different, more solid with colors. How does that work? Is it the chaos game again?
No, for those, it's typically a different method called the escape time algorithm. It works pixel by pixel.
Okay.
For every single point or pixel on the screen, you take its corresponding complex number value and you repeatedly apply the generating function.
Yeah.
The famous one for Mandelbrot is Zila goes to Ziler plus Ziler. You do that over and over.
Iterate again.
Right. And then you check how quickly the result escapes a certain boundary, usually a circle of radius 2 in the complex plane.
Escapes, like flies off to infinity.
Essentially, yes. If the magnitude of the number gets bigger than 2, we know it will fly off to infinity if we keep iterating. So if it escapes before some maximum number of iterations we set, we color that starting pixel based on how many iterations it took to escape. Faster escape, maybe one color. Slower escape, another color.
And if it doesn't escape?
If it stays bounded, never getting bigger than 2, even after many iterations, it's considered inside the set. Those points are usually colored black.
Ah, so that's how you get those intricate colored patterns. The colors show the speed of escape.
Exactly. That relatively simple idea creates those incredibly detailed, vibrant images we see with all the swirls and filaments showing different escape speeds and pathways.
Okay, so we can generate them from simple rules, visualize them with these cool algorithms, but how do we measure their complexity? You said they're not smooth like normal shapes. Does regular measurement even work?
That's a key point. Traditional measurements, like length, area, volume, they're based on Euclidean geometry. Fractals break that mold. They have what's called a non-integer fractal dimension.
Non-integer dimension, like dimension 1.5.
Precisely like that. It's a way to actually quantify their roughness or complexity. It describes how densely the fractal fills space compared to, a line dimension 1, a plane dimension 2, or a solid dimension 3.
How do you calculate that? Is there one way?
Well, the most theoretically solid definition is the Hausdorff dimension. But honestly, it's often really hard to calculate directly.
Okay.
So in practice, people often use the box counting dimension. It's more practical computationally. You basically cover the fractal with boxes of a certain size, count how many you need. Then you use smaller boxes, count again. You repeat this with smaller and smaller boxes, and the way the number of boxes changes as the size decreases gives you an estimate of the fractal dimension.
Covering it with boxes, I can sort of visualize that.
Yeah, and for fractals that are strictly self-similar, like the Sierpinski triangle where the pieces are exact scaled copies, there's sometimes an even simpler formula called the similarity dimension. It directly relates the number of copies and their scaling factor to the dimension. But the main takeaway is this non-integer dimension. It's a defining feature, a number that captures that infinite detail.
Okay, wow. That's a lot to take in. They're just about fractals themselves. Really fascinating. Now, let's switch gears a bit to the other side of this equation. Deep generative models. How does AI, specifically these models, how do they learn patterns and then just conjure up new stuff, new data that looks real but wasn't explicitly put in? What's the goal there?
Right. So deep generative models are really the creative engine in modern AI. Their main goal, their purpose, is to learn the underlying patterns, the sort of probability distribution of a data set they're trained on.
Learn the distribution. Okay.
Yeah. And once they've got a good grasp of that underlying structure, they can then generate brand new synthetic data samples that look like they could have come from the original set. They've totally changed fields like image generation, going way beyond just classifying images, saying that's a cat, to actually creating images of cats that have never existed before.
So creating brand new things. Got it.
And in this space, we're mostly going to focus on 3 big families of these models that are really prominent right now.
Okay, let's start with the one I think most people have heard of, generative adversarial networks, GANs. They've been huge for a while. How do they actually work? And why are they so good at making realistic pictures? But also, what's the catch?
GANs are based on this really ingenious idea, almost like a game between 2 AIs. It's an adversarial training process. You have 2 neural networks competing.
2 networks.
Yeah. One is the generator, let's call it Chia. It takes random noise, like digital static, as an input and tries to turn it into fake data, like a fake fractal image in our case, that looks totally real.
Okay, the artist or forger.
Kind of, yeah. And the other network is the discriminator. Its job is to be the critic or the detective. It looks at both real images from the training data set and the fake images from the generator, and it tries to tell them apart. It tries to spot the fakes.
So one makes fakes, the other tries to catch them.
Exactly. And they're locked into this constant battle, what's called the zero-sum minimax game. The generator wants to get better at fooling the discriminator, making its fakes more convincing. The discriminator wants to get better at detecting the fakes.
A constant arms race.
Precisely. This competition forces the generator to produce images that are increasingly realistic, incredibly detailed. That's their big strength. They can produce exceptionally sharp and high-fidelity images. They often achieve state-of-the-art photorealism. Plus, once they're trained, making a new image inference is usually very fast.
Okay, sharp images, fast generation, sounds great. What are the downsides then? The Achilles heels?
Well, the training process itself. It's notoriously unstable and difficult.
Yeah.
Getting these 2 networks to reach a nice balance called convergence can be really tricky. It sometimes feels more like an art than a science.
Finicky.
Very. And a really common problem is called mode collapse.
Mode collapse.
Yeah, it's where the generator figures out just one or maybe a few kinds of images that are really good at fooling the discriminator, and then it just keeps making only those images over and over again.
So it doesn't learn the full variety of the data, just finds a few tricks that work.
Exactly. It collapses onto just a few modes or types of output. So you lose diversity, which is often what you want from a generative model. It's like a musician who only plays one hit song.
Right, that makes sense. Okay, so GANs are sharp but tricky. What about the next type? Variational autoencoders, or VAEs. They sound different just from the name.
They're built on a different idea, yeah. VAEs combine an autoencoder structure which learns to compress and then reconstruct data with probability theory. A VAE has 2 main parts, an encoder and a decoder.
Like a regular autoencoder.
Sort of, but with a twist. The encoder takes an input image, but instead of mapping it to a single fixed point in a compressed space, it maps it to the parameters, typically the mean and variance of a probability distribution within a probabilistic latent space.
Whoa. Okay. Probabilistic latent space. Parameters of a distribution. Can you break that down a bit? Sounds less like a point and more like a fuzzy region.
That's a great way to think about it. Yeah, the encoder doesn't just give you one compressed code. It describes a whole distribution of possibilities in this hidden, lower dimensional latent space. Think of it like a map where similar images don't map to single points, but to nearby, overlapping fuzzy regions or clouds.
Okay, fuzzy clouds of concepts. Then what?
Then the decoder takes a random sample drawn from that specific fuzzy cloud in the latent space, and it tries to reconstruct the original input image from that random sample.
A random sample. How does the network even learn if there's randomness involved? Doesn't that mess up the training?
That's where a clever mathematical trick comes in, called the ray parameterization trick. It's a bit technical, but it essentially allows the network to learn efficiently through that random sampling step. It makes the whole probabilistic process differentiable, so we can use standard training methods like backpropagation.
Okay, magic math trick. Got it.
Yeah.
And the goal of this whole setup?
The overall aim is to learn a latent space that is smooth and continuous. This means that if you move smoothly between points or distributions in this latent space, the images generated by the decoder should also transition smoothly and meaningfully.
So you could morph one image into another just by walking through this latent space.
Exactly. That's one of the big strengths of the AEs. They are generally more stable to train than GANs, and they excel at learning this really well-structured, smooth, latent space. This makes them fantastic for things like blending concepts together or exploring variations on a theme just by navigating this space.
That sounds really useful. What's the downside compared to GANs?
The main drawback is usually image quality. VAE-generated images are often blurrier, less crisp than the best GAN outputs. It's thought to be partly due to the way they're trained, often using loss functions that encourage averaging, which can smooth out fine details.
Right, blurriness might be a problem if you want super intricate fractals. Okay, so GANs are sharp but unstable. VAEs are stable and smooth but blurry. What about the third type, the newer ones? Denoising diffusion probabilistic models, DDPMs. They seem to be everywhere lately.
They're definitely the current stars in many areas, yeah. DDPMs, or diffusion models, work on a really elegant concept. A two-stage process of diffusion and reversal.
Diffusion and reversal, like noise.
Exactly like noise. The forward diffusion process is fixed, not learned. It takes a real image and gradually adds a tiny bit of noise, step by step, over hundreds or thousands of steps, until the original image is completely overwhelmed and becomes pure random noise, like dissolving a photo into TV static.
Okay, so you destroy the image methodically. Why?
Because the magic happens in the learned reverse process. Here, a neural network learns to undo that diffusion. It starts with pure noise, just random static, and then it iteratively predicts the noise that was added at the last step of the forward process and subtracts it. Step by step, it gradually removes the noise, effectively reversing the diffusion until a clean, high-quality image emerges from the chaos.
Wow, so it learns to denoise its way back to an image.
Precisely. It learns the path from noise back to data. It's an incredibly clever way to model the data distribution.
Okay, that sounds powerful. What are the pros and cons?
The biggest pro is state-of-the-art performance. Diffusion models often produce images with incredible sample quality and diversity, frequently beating both GANs and VAEs on many benchmarks. They look amazing. Plus, their training is generally stable, much more so than GANs.
Stable training, top quality. Sounds perfect. What's the catch this time?
The catch is speed, specifically inference speed. Generating a single image requires running the denoiser network potentially hundreds or thousands of times, once for each step of the reverse process. This makes them typically much slower to generate an image compared to GANs or even VAEs, which can often produce an image in a single forward pass.
So quality comes at the cost of time and computation.
Makes sense.
It's a significant trade-off, yeah.
Okay, so if we try to make a quick comparison, a sort of taxonomy, GANs are sharp, fast to generate, but unstable and risk mode collapse. VAEs are stable, give you that nice, smooth, latent space for blending, but tend to be blurry. And DDPMs give top-tier quality and diversity with stable training, but they're slow to actually generate the images.
That's a really good summary of the main trade-offs. There's no single best model for everything. The choice really depends on what you prioritize for your specific task: image fidelity, diversity, generation speed, training stability, the need for a smooth, latent space. It's a balancing act. Right. Okay, that gives us a solid grounding in both fractals and these generative AI powerhouses. Now let's finally connect them. The first main way people are doing this fractal hybrid AI thing is what you call the data-driven approach, often making pseudo-fractals. What exactly is a pseudo-fractal, and how does an AI learn to make one?
Yeah, this data-driven path is really the most direct or foundational way to combine them. A pseudo-fractal essentially is an image that looks like a fractal. It captures the visual style, the textures, the intricate patterns you see in mathematically generated fractals.
It looks like one, but isn't necessarily generated by the same math rules.
Exactly. That's the key distinction. True mathematical fractals get their infinite detail and self-similarity from those recursive math formulas we talked about. Pseudo-fractals, on the other hand, are generated by an AI model that has learned the appearance of fractals from a dataset, but not necessarily the underlying mathematical process.
So the AI is like an artist mimicking the style, rather than a mathematician deriving the form.
That's a great analogy, yes. The AI learns the visual grammar of fractals, the common motifs, the textures, but it doesn't inherently understand or execute the recursive logic that originally created them. It's learning by looking, not by calculating the fractal math itself.
Okay, that makes sense. So how does this work in practice? What are the steps involved in getting an AI to generate these pseudofractals?
It follows a pretty standard machine learning pipeline, much like training other types of generative models. The absolute first and maybe most critical step is dataset generation. You need a lot of fractal images to train the AI.
Where do you get those? Just download them?
Usually you have to generate them yourself algorithmically. You use the known mathematical formulas for things like the Mandelbrot set, various Julia sets, maybe some IFS fractals, and you generate thousands, maybe millions of examples. The key is to make the dataset really large and diverse. Different zoom levels, different colorings, different parameters, so the AI gets exposed to a wide range of fractal structures.
Right, you need good ingredients. A diverse dataset gives the AI more to learn from.
Absolutely.
Yeah.
Without that diversity, the model might not generalize well. Or it might fall into that mode collapse issue we discussed with Jans, just learning to make one type of fractal look alike.
Okay, so you generate this massive fractal library. What then? Just feed it straight into the AI?
Not quite yet. There's a crucial step: data preprocessing and augmentation. You need to get the images ready for the network.
Pre-processing, like resizing them.
Yeah, resize is part of it. All images usually need to be the same dimensions to fit the model's input layer. And normalization is important too, scaling the pixel values, maybe between 0 and 1 or -1 and 1. This helps the network train more stably and often faster.
Okay, standard stuff. But what's data augmentation? Why do you need that if you already generated tons of fractals? Aren't you just making copies?
Data augmentation is a really clever technique to make the training more robust and prevent the AI from just memorizing the training images. That's called overfitting.
Right, overfitting.
So you artificially increase the variety in the dataset without needing new fractals. You take the existing fractal images and apply random transformations. Maybe rotate them slightly, shift them a bit horizontally or vertically, zoom in or out a little, flip them.
Why does that help?
It forces the AI to learn the inherent structural properties of the fractals, regardless of their specific position or orientation in the image. It has to recognize the fractalness, even if it's tilted or shifted. This helps the model generalize better, meaning it's more likely to create truly novel pseudofractals later, rather than just slightly modified copies of what it saw during training.
Okay, that's smart. Making the training harder forces the AI to learn the deeper patterns. So data prepped and augmented. Now you train the generative model, like a JAN or a VAE.
Exactly. You feed this prepared dataset into your chosen generative model. Could be a JAN, could be a VAE, or even a diffusion model, which are also state-of-the-art here.
And what happens during training?
Well, if it's a JAN, the generator learns to produce images from noise that look like the fractals in the dataset, while the discriminator tries to tell the difference. That adversarial process pushes the generator to get better and better at mimicking the fractal aesthetics.
Okay, and if it's a VAE?
With a VAE, the encoder learns to map the fractal images into that smooth latent space we talked about, and the decoder learns to reconstruct them. The goal here is to learn a good probability distribution that represents the space of possible fractals seen in the data. This is great for exploring variations and blending different fractal styles.
Right, and diffusion models would learn that denoising process we discussed.
Precisely. They'd learn to generate fractal-like images by starting with noise and gradually refining it based on the patterns learned from the dataset.
So what's the ultimate goal? What kind of images are you hoping to get out of this whole data-driven process?
The main aim is to create these pseudo-fractals, novel visual forms that, ideally, retain some of the essential properties we associate with mathematical fractals, like apparent self-similarity and intricate detail. But crucially, they should also incorporate unique variations and stylistic elements that arise from the AI's learning process itself. You're hoping the AI doesn't just copy, but maybe combines features, abstracts patterns, or introduces textures in ways that are different from traditional, purely mathematical fractal generation. It's about bridging algorithmic generation with AI creativity.
So potentially generating patterns that are fractal-like, but maybe couldn't be easily made with just the standard math formulas?
That's the exciting possibility, yeah, expanding the aesthetic space.
Okay, so the AI makes these pseudo-fractals. How do you actually check if they're any good? How do you know if they've really captured those fractal properties, or if they're just, pretty noise?
That's a really important step, analysis and verification. First, there's just visual inspection. You look at the generated images. Do they look like fractals? Do you see repeating motifs, self-similar patterns, intricate details? It's a qualitative check.
The eye test.
Exactly. But you need more than that. So quantitative analysis is critical. A key technique here is using the box counting method, which we mentioned earlier, for calculating fractal dimension.
Right, covering it with boxes.
Yeah. You apply that method to the generated pseudo-fractal images. You calculate their fractal dimension and compare it to the dimensions of the original mathematical fractals in the training set. This gives you a numerical way to see if the AI has actually captured that characteristic geometric complexity, that space-filling property.
Okay, so you can measure if it's quantitatively similar in complexity. What about understanding how the AI is organizing its knowledge of fractals? Can you peek inside its brain, so to speak?
Yes, and that's where latent space exploration becomes really insightful, especially for models like VAEs.
Because they have that explicit, smooth, latent space.
Precisely. With a VAE, you can perform interpolation. You pick 2 points in the latent space that correspond to 2 different generated fractals. Then you generate images from points along a straight line path between those 2 points in the latent space.
And what do you see?
If the model has learned a good, coherent representation, you should see a smooth, meaningful transition between the 2 fractal forms in the generated images. You might see one style gradually morph into another. This shows the model hasn't just memorized points, but has learned a continuous map of fractal concepts.
That sounds incredibly cool, like watching one fractal melt into another based on the AI's understanding.
It really is. It gives you confidence that the model has learned something meaningful about the underlying structure.
What about GANs? Their latent space is usually just random noise input, right? Can you still explore it in a meaningful way?
It's a bit different, yeah, because the input noise space for a GAN isn't inherently structured in the same way as a VAE's latent space. But you can still do interesting things with vector arithmetic on the input noise vectors.
Vector arithmetic, like adding and subtracting the noise code.
Exactly. Researchers sometimes find that certain directions or vectors in that high-dimensional noise space correspond to semantic features in the output image. For example, maybe adding a specific noise vector consistently makes the generated fractal look more spiky, while subtracting it makes it more swirly or more branched.
So you can find control knobs in the noise itself.
Potentially, yes. Discovering these relationships allows for manipulating semantic attributes of the generated fractals. It offers a pathway towards more controllable, interactive fractal generation systems, where you're not just rolling the dice with random noise, but actively steering the generation towards desired features. It gives insights into how the AI encodes these concepts and points towards more human-AI collaborative creativity.
Being able to control spikiness or curliness directly, that definitely feels like a big step beyond just random generation.
Okay, so that covers the data-driven path, learning from examples. Now, let's talk about the other approach you mentioned, the architecturally driven one, using things like fractal generative models, FGMs. This sounds fundamentally different, like it's changing the AI itself.
It is fundamentally different, yes.
This approach is arguably more profound, maybe even paradigm shifting. Instead of just feeding fractal images to a standard AI model, the idea here is to embed fractal principles directly into the model's architecture. The AI itself is built with fractal-like properties.
The AI is built like a fractal. How does that even work?
It draws inspiration from, well, fractals in nature, obviously, but also things like the hierarchical structure we see in biological brains. The core concept is recursive modularity and self-similarity at the architectural level.
Recursive modularity. Okay, can you unpack that?
Sure. Imagine you design a basic building block, an atomic generative module. This module is itself a small generative model. Then, you design the architecture so that this atomic module can recursively invoke copies of itself, child modules.
So, A model made of smaller versions of itself.
Essentially, yes.
Yeah.
You create this deep hierarchical structure where the same basic pattern repeats at different scales within the network architecture. This gives the model an inherent self-similarity across its architectural levels, mirroring how mathematical fractals are built.
Okay, I think I'm getting the concept. What's the advantage of building an AI like this?
One huge advantage is efficiency, particularly in how complexity scales. Because of this recursive structure, you can achieve an exponential growth in the complexity and detail the model can handle, like output image resolution, with only a linear increase in the number of recursive levels or depth. Add one more layer of recursion, and the capability jumps dramatically, but the increase in parameters or computation might be relatively modest.
Exponential complexity growth with linear cost. That sounds incredibly efficient, especially for high-resolution stuff that usually kills standard models. What kind of speed-ups are we talking about?
The efficiency gains can be really significant. Some research suggests an FGM could be up to like 96 times faster than a comparable traditional model, like a visual autoregressive or VAR model, when generating images at, say, 255 by 256 resolution.
4,000 times faster. That's staggering. What's the mechanism behind that speed-up?
It comes down to how they handle the image generation, especially for models that generate pixel by pixel, which is usually very slow because the computation scales quadratically with the image size. FGMs use a kind of divide and conquer strategy.
Right.
They break the image down hierarchically into smaller patches. Generation starts at the top, coarsest level, maybe dealing with large patches. Then information flows down to child models, each responsible for generating a finer resolution patch within its parent's area, adding more detail recursively.
So it builds the image up in levels of detail.
Right. And the key to the efficiency is that the attention mechanism, which is often the computational bottleneck in these models, operates locally within each small patch, rather than having to look at the entire huge image grid all at once. This localized processing dramatically cuts down the computation needed.
Local attention on patches. Okay, that makes intuitive sense for why it would be faster. So, massive speed up. How do they actually perform on benchmarks? Are the images as good as GANs or diffusion models, even if they're faster?
That's the crucial question. FGMs have shown really strong performance in likelihood estimation. For instance, getting state-of-the-art scores on datasets like CFAR10 for metrics like negative log likelihood. This suggests they're very good at modeling the underlying probability distribution of the data accurately.
Okay, good at modeling the data, but the pictures?
The image quality is generally high, competitive on benchmarks like ImageNet. However, based on current research, while the quality is good, it doesn't yet consistently surpass the absolute best results from top-tier GANs or diffusion models when measured by things like FID, Fréchet inception distance, or IS, inception score.
So there's still a bit of a quality gap compared to the very best image generators.
It seems that way currently. Some metrics suggest high fidelity, like IS, but others might indicate they don't capture the full diversity of the training data quite as well, like FID or recall, as the leading GANs or diffusion models yet. There's a viewpoint that maybe FGMs are best seen as highly efficient, accelerated versions of existing autoregressive models, rather than a completely new paradigm in terms of ultimate image quality. Bridging that final quality gap is still an active area of research.
Interesting. So incredible efficiency, strong modeling, good quality, but maybe not peak quality just yet. Still, embedding fractal logic in the architecture itself, that feels like a really powerful idea.
It absolutely is. It provides a strong inductive bias, a built-in assumption that's well-suited for modeling the complex, multi-scale structures we see everywhere in nature.
Yeah.
It's a fundamentally different way to think about generative AI design.
Okay, we've explored these two fascinating paths for bringing fractals and AI together. Now let's pivot to the roadblocks. What are the really big challenges holding this field back? You mentioned something called the fractal inverse problem. What is that, and why is it such a beast?
Right, the fractal inverse problem is a major persistent headache in this area. Basically, it's the task of taking a finished fractal image, you see the beautiful pattern, and trying to work backward to find the exact mathematical rules, like the precise iterated function system, IFS parameters, that created it.
So going from the picture back to the recipe.
Exactly. It's the inverse of the normal process, where you start with the rules, the recipe, and generate the image, the cake. Your analogy earlier was perfect, trying to perfectly reverse engineer a complex cake just by tasting it. You know the ingredients are in there, but figuring out the exact amounts and steps is incredibly difficult.
Why is it so hard for computers? It seems like pattern recognition, which AI is usually good at.
It's incredibly hard because the problem has been mathematically proven to be NP hard.
NP hard, I've heard that term. It means really, really difficult.
Essentially, yes. In practical terms, it means there's no known efficient algorithm that can guarantee finding the absolutely perfect optimal solution in a reasonable amount of time, especially for complex fractals. The computational effort needed just blows up exponentially as the fractal gets more intricate.
So an exhaustive search is just impossible.
Pretty much, yeah. It would take lifetimes, even on supercomputers. This forces us to rely on finding good approximations rather than the perfect, exact mathematical recipe.
Okay, so if finding the perfect answer is basically off the table for complex cases, how do researchers even try to tackle this? What are these approximation methods that get you close?
Since perfection is out, the focus shifts to optimization techniques that find good enough solutions. One popular approach uses genetic algorithms, GAs.
Genetic algorithms, like survival of the fittest for fractal recipes.
That's a fantastic way to put it, yes. GAs are inspired by natural selection. You start with a population of random candidate solutions, different sets of IFS parameters, maybe.
That's your potential recipe.
Exactly. Then you evaluate how fit each one is, how well the fractal generated by those parameters matches the target image you're trying to reverse engineer. The better the match, the higher the fitness. Then you select the fitter solutions to reproduce. They undergo crossover, where parts of two good solutions are mixed together to create new offspring solutions, and mutation, where small, random changes are introduced to keep things diverse and explore new possibilities. You repeat this process over many generations, and hopefully the population evolves towards better and better approximations of the true recipe.
Breeding fractal recipes, that's really cool. Are there other techniques like that, inspired by nature maybe?
There are. Another powerful heuristic method is simulated annealing, or FA.
Simulated annealing. Sounds like metalworking.
The analogy comes directly from annealing in metallurgy, yeah. Heating metal and cooling it very slowly to get a strong, stable structure. In the algorithm, you start with a candidate solution, IFS recipe, and randomly tweak it slightly. If the tweak improves the match to the target fractal, lower error, you always accept it.
Makes sense. Keep the good changes.
Right. But here's the clever part. Even if the tweak makes the solution worse, higher error, you might still accept it, especially early in the process when the algorithm's temperature parameter is high.
Accept a worse solution. Why?
To avoid getting stuck. Sometimes, to find the best overall solution, the global minimum error, you first have to go slightly uphill, escaping a worse but locally good solution, a local minimum. As the algorithm progresses, the temperature gradually cools, making it less and less likely to accept bad moves. This allows it to explore the solution space more broadly initially, then settle down towards a good minimum.
Okay. A probabilistic way to avoid getting stuck in the first okay-ish answer it finds. Clever. Are there newer methods too, maybe using neural networks directly?
Yes, definitely. More recently, people have started using neural network approaches, specifically training convolutional neural networks, CNNs, which are great at analyzing images to try and directly predict the IFS parameters just by looking at the input fractal image.
So the CNN looks at the picture and spits out the recipe.
Sort of, yes. The predictions are usually approximate, not perfectly accurate. But the big advantage is that CNNs can make these predictions very quickly, much faster than running a long GA or SA optimization.
So they're good for a first guess.
Exactly. They can provide excellent initial guesses or starting points, which can then be fine-tuned using those other slower but potentially more accurate optimization methods like GA or SA. It helps speed up the whole process considerably.
And you mentioned a theoretical tool, something about a collage.
Right, the collage theorem. It's more a theoretical underpinning than a direct algorithm. Yeah. It basically says that if you can find a set of contractive transformations, your IFS rules, such that if you apply them all to the target fractal image itself and piece together the results, making a collage, and that collage looks very similar to the original target image, then the actual attractor of that IFS will also be very close to the target image.
Okay. So if you can make a good collage of the target using the rules themselves will generate something close to the target.
That's the essence of it. It helps justify why minimizing the difference between the target and its collage is a valid approach for finding the right IFS parameters, even though finding the best collage is still the hard part.
Okay, the inverse problem is clearly a massive hurdle. Beyond that, what about just evaluating how well these fractal hybrid AI models are doing? You hinted standard metrics might not work well. Why not?
You're right, that's another critical challenge. The lack of suitable evaluation metrics. The standard tools we use to judge AI-generated images are often really poorly suited for fractals.
Like what kind of metrics?
Well, things like PSNR, peak signal-to-noise ratio, and SSIM, structural similarity index. They basically compare images pixel by pixel, or look at local structural similarities to a reference image.
Okay. Why is that bad for fractals?
Because they don't really capture what makes a fractal interesting. They're focused on pixel-level accuracy or similarity to one specific reference. They don't measure the emergent complexity, the self-similarity across scales, or even just the overall aesthetic quality as judged by a human. A generated fractal could be visually stunning and have clear fractal properties, but still get a poor PSNR score if it doesn't match some reference pixel perfectly.
Right, they're too literal. What about the more advanced metrics people use for GANs, like inception score or FID? They look at distributions, not just pixels. Do they work better?
Unfortunately, not much better for fractals. Inception score, IS, and first inception distance, FID, work by comparing the statistical distribution of features in generated images to features in real images, using a pre-trained network like InceptionNet, which is usually trained on datasets like ImageNet, millions of photos of objects, animals, scenes.
Okay, so what's the problem?
The problem is that these metrics are fundamentally designed to assess photorealism and semantic diversity in natural images. They reward images that look like typical photographs. They do not care about or measure the unique geometric properties of fractals like true mathematical self-similarity, infinite detail, or fractal dimension.
So a perfect fractal might actually score badly.
It absolutely could. A mathematically perfect, intricate fractal might get a terrible FID score simply because its structure is completely alien to the distribution of ImageNet photos. The metric might see it as unrealistic or low quality just because it doesn't look like a cat or a car.
Wow, so the tools are measuring the wrong thing entirely.
It highlights a fundamental mismatch. We're trying to evaluate a unique geometric art form using tools designed for photographic realism. It's a major blind spot.
That seems like a huge problem for actually making progress. If your measurement tools are broken, how do you know if you're improving? Does this connect to how humans actually see these things?
Absolutely. This leads right into the lack of perception-based evaluation. Current metrics totally ignore how humans actually perceive and process these incredibly complex patterns. For instance, they don't consider the cognitive load.
Cognitive load, like how much mental effort it takes.
Exactly. How much mental effort is required to look at and understand the image. Cognitive load theory breaks this down. There's intrinsic load, which is just the inherent complexity of the fractal itself, a really detailed zoom. Mandelbrot zoom has high intrinsic load. There's extraneous load, which comes from bad presentation, like a poorly generated, messy pseudo-fractal might add unnecessary mental clutter. And then there's germane load, which is the useful effort involved in actually understanding the structure. Current metrics tell us nothing about how well a generated fractal manages its intrinsic complexity to minimize that extraneous, unhelpful load. We need new fractal-specific evaluation metrics. Metrics that can actually quantify geometric properties like fractal dimension automatically from the image, and metrics based on human perception, maybe through user studies asking about aesthetic appeal, perceived complexity, and yes, cognitive load. We need to measure if the AI is creating something humans find compelling and comprehensible in its complexity.
Right, measuring both the math and the human response. That makes a lot of sense. Okay, so technical challenges, evaluation challenges. What about the bigger picture? Legal stuff, ethical stuff. Training these AIs needs tons of data. Generating art raises ownership questions. It must be a minefield.
It absolutely is a minefield, and a rapidly shifting one. Data privacy is a huge issue right off the bat.
Because the models need so much training data.
Exactly. Generative AI models are incredibly data hungry. They're often trained on massive data sets scraped from all over the internet. This immediately bumps up against regulations like GDPR in Europe or CCPA in California.
How so?
Well, those laws have strict rules about how you can collect and use personal data. You need a lawful basis for processing it, you need to stick to the specific purpose it was collected for, purpose limitation, and you should only collect what's necessary, data minimization. Training a giant model on scraped web data often doesn't align neatly with those principles.
And what about people's rights, like the right to have your data deleted, the right to be forgotten? How does that work with AI? Can't they just delete the data points?
If only it were that simple. The right to erasure is a major technical headache for AI. Once data has been used to train a big neural network, its influence gets baked into potentially billions of tiny adjustments across the network's weights. It's not like deleting a row in a database.
So the data is kind of smeared throughout the model.
That's a good way to put it. Figuring out how to surgically remove the influence of one person's data without completely retraining the model from scratch, which is insanely expensive, is a really difficult and mostly unsolved technical problem. It creates this fundamental tension between legal rights and how deep learning models currently work.
Wow, okay. Baked in data, that's a big compliance challenge. Then there's the other big one, copyright. AI can generate amazing art now. Who owns it? Especially with fractals, which are often math-based anyway.
Copyright is incredibly complex and evolving fast. The core issue in places like the US revolves around the human authorship doctrine.
Meaning a human has to create it.
Generally, yes. U.S. copyright law requires human authorship for protection. This was central to a recent case, Thellery Perlmutter in 2025, which basically ruled that art generated purely by AI, without significant human creative input, lacked a human author and therefore couldn't be copyrighted. It might just fall into the public domain.
Public domain. So anyone could use it. That might discourage people from using AI to create if they can't own it.
That's exactly the concern, yeah. It could disincentivize creation if there's no protection.
So what counts as enough human input then? Is just typing a prompt enough for me to own the copyright?
Probably not, based on current guidance. The U.S. Copyright Office suggests it requires significant creative control by the human over the final work's expression. This likely means more than just a simple prompt. It might involve things like iteratively refining the output, selecting specific AI-generated elements, arranging them in a creative way, significantly modifying the AI's output, essentially transforming it through substantial human creativity.
So the human has to be more like a director or editor, not just someone who pushes a button.
That seems to be the direction things are heading, yes. And this is separate from the other huge copyright issue, the training data. There are massive lawsuits happening right now about whether AI companies infringed copyright by trading their models on vast amounts of copyrighted text and images scraped from the web. The companies often argue it's fair use, but creators disagree. The outcome of those cases will be huge for the whole field.
Right, fair use versus mass infringement, a massive legal battle. Okay, so privacy and copyright are clearly huge ongoing issues. Are there broader ethical things to think about too, beyond just the law, as these fractal AIs get better?
Absolutely. We can draw parallels from ethical guidelines developed in other fields that use AI, like the APA guidelines for AI in psychology. Even though they're for psychologists, the principles are relevant.
Like what?
Things like ensuring confidentiality and data privacy throughout the AI lifecycle. Actively working to identify and mitigate bias in the models and their outputs, AI can easily pick up and amplify biases from its training data. Promoting transparency and explainability, trying to understand why the AI generates what it does, tackling that black box problem, and crucially, ensuring human oversight and judgment.
Human oversight, meaning the AI shouldn't be completely autonomous?
Right. The core ethical stance should be that AI augments human capabilities. It doesn't replace human judgment or creativity entirely. The human creator, the human user, needs to remain in control, using AI as an incredibly powerful tool, but not abdicating responsibility to it. It's about accountability and building trustworthy systems.
Okay, so we've mapped out the landscape. The cool tech, the data path, the architectural path, and the significant challenges, technical, evaluative, legal, ethical. Where do we go from here? What are the key future pathways or recommendations to actually push fractal hybrid AI forward?
There are several promising directions, yeah. One big one is advancing semantic fractal correspondence.
Semantic fractal? You mean linking the math controls to things humans understand?
Exactly. Right now, controlling fractal generation often involves tweaking abstract mathematical parameters. The goal is to bridge that gap so artists or designers can control more intuitive, human-understandable semantic features. Things like make it more branched, increase the curliness, adjust the level of fine detail, rather than just changing parameter C or transformation matrix 3.
Wow. Making it more like talking to an artistic collaborator than programming a function.
Precisely. How do we achieve that?
Yeah.
Well, continued research into latent space disentanglement and interpretation for VAEs and JANs is key, trying to isolate specific dimensions in the latent space that reliably control these semantic features. Maybe using existing computer vision knowledge about how fractal features correlate with semantic content, like texture describing roughness or smoothness. And then there are more speculative ideas, like developing spectral fractal symbolic interfaces, trying to directly link network properties to symbolic meanings for truly high-level control. Imagine telling the AI, make the fractal feel more serene, and it actually adjusts the underlying parameters accordingly.
Make it more serene. That would be amazing. Okay, so better control. What about the AI architectures themselves? We talked about FGMs being efficient. What's next there?
Architectural innovation is definitely a huge area. Building on that FGM idea of recursive modules, researchers should explore using alternative atomic modules. What if the basic building block wasn't just a simple autoregressive model, but maybe a mini diffusion model or a mini VAE? Could you get fractal diffusion models or fractal VAEs, combining the efficiency of the fractal structure with the specific strengths of those other generative paradigms?
So hybridizing the architectures themselves.
Exactly. And perhaps even more exciting is the idea of true hybrid architectures that explicitly combine the data-driven and architecturally driven approaches. Imagine, for instance, an FGM that doesn't just generate pixels, but operates within the learned, semantically meaningful, latent space of a pre-trained VAE.
Whoa. So the fractal structure generates concepts in the VAE's mind.
Something like that.
Yeah.
You could potentially get the best of both worlds. The efficient, structured generation of FGMs combined with the semantic understanding and smooth interpolation power of VAEs. That could be incredibly powerful.
That does sound powerful. And given all the problems with current metrics, we obviously need better ways to measure progress, right?
Absolutely critical. We need unified evaluation frameworks. This means a dedicated effort to develop a whole new suite of fractal-specific metrics.
What would those include?
Several things. Geometric metrics, like automated tools to calculate fractal dimension or other measures of self-similarity directly from the generated images. Crucially, perceptual and cognitive metrics. This means running user studies, grounded in cognitive science, to actually measure aesthetic appeal, perceive visual complexity, and that cognitive load we talk about, how easy or difficult is it for a human to process the image. And finally, controllability metrics, ways to quantitatively measure how well a model responds when you try to control those semantic attributes like spikiness or branch density.
So a whole toolkit of new metrics.
Yes. And alongside that, the field really needs a fractal hybrid benchmark dataset. A large, standardized, well-annotated dataset with diverse mathematical fractals where we know the ground truth parameters, maybe natural images with fractal properties, all labeled with geometric info and maybe even semantic tags. This would allow researchers everywhere to compare their models fairly on the same playing field.
Standardizing the evaluation makes perfect sense. What about that super hard fractal inverse problem? Is there any hope AI could eventually crack it, maybe leading to applications beyond just art?
It's definitely worth revisiting with modern AI. While proving it NP hard means no perfect, efficient general solution, AI might get incredibly good at finding extremely accurate approximations, potentially better than GAs or SA alone. Imagine training a powerful conditional generative model. You feed it a fractal image, and it learns to output the most likely IFS parameters that generated it, trained to minimize the reconstruction error.
So AI learns to guess the recipe really well.
Exactly. And if it gets good enough, this could lead to totally new AI-powered compression algorithms.
Compression.
Because the IFS parameters of the recipe are often incredibly compact, just a few numbers. If AI can reliably extract those parameters from a complex image, you've essentially compressed the image down to that tiny set of numbers. It could be a revolutionary way to store or transmit complex visual information, leveraging the inherent compressibility of fractal structures.
Storing images as tiny mathematical recipes. Fascinating. Okay, and lastly, tackling that legal and ethical mess. How can research proactively address privacy, copyright, bias, instead of just reacting when problems blow up?
Proactive engagement is vital. Research needs to focus on developing technical solutions for legal ambiguity. For example, using explainable AI, XAI methods. Could XAI tools document the specific creative contributions of the human versus the AI in generating a piece? That could directly help with copyright claims for AI-assisted art by providing evidence of human authorship.
Using AI to document the human's role. Interesting.
Also, developing robust systems for data provenance and watermarking. Provenance means being able to trace where the training data came from, ensuring it was properly licensed. Watermarking means embedding invisible but detectable signals into AI-generated content to clearly identify it as AI-made. This increases transparency and accountability.
So you can tell if an image was AI-generated and maybe trace its origins.
Right. And beyond specific tools, it's about building ethical considerations like bias detection and mitigation, fairness, transparency into the core design and development practices for these models from the very beginning, not just as an afterthought, moving from reactive fixes to proactive, responsible innovation.
This whole deep dive, it really drives home how AI isn't just learning to copy fractals, but maybe starting to internalize or even embody a kind of fractal logic. You know, that logic that mirrors the complexity we see all through nature. It really makes you wonder, and this is maybe a final thought for you, the listener, to chew on. As these AI systems get better at processing and generating patterns that echo nature's complexity, that self-organizing recursive quality, what truly new forms of intelligence, maybe? Or even completely novel kinds of creativity? What might emerge from that synthesis?
That is a really profound question to end with.
Yeah.
Seriously, think about that. What happens when our machines start, in a sense, thinking in fractals? Using that kind of recursive, multi-scale logic, could it lead to insights or creations that are just fundamentally different from how humans think and create?
Maybe even solve problems in ways we can't conceive of right now.
Possibly. It's definitely something fascinating to keep an eye on as this field evolves. It's constantly pushing at the edges of what we think of as art, and maybe, just maybe, what we think of as intelligence itself.